Hello everyone. Today we will discuss a kind of binary tree which is called heap. We will discuss about a kind of binary tree which is called a heap, and the operation we will perform an operation on this heap. The operation is how to insert an element into a heap. Now, heap is a binary tree. Binary tree means every node can have at most two children. There may be one children, or at most there can be two children. So heap is a kind of binary tree where every node in this tree have only one or two children, not more than two. And the nodes which has no child, that is called leaf node, and the node which has at least one child, it's called internal node, and the node of the tree which has no parent, that is called the root node of the tree. So we will now heap is a type of binary tree which satisfy some properties means, if we take example of a tree which is a heap, so every node in this tree, the value in every node in this tree will have is greater than all of its children. If we take every node in a heap, then every node which has children, that parent node has always greater value than all of its children, and this property is maintained for every node in the tree, in a binary tree, then that binary tree is called heap. So for example, we will discuss about this heap and the operation on heap which we will perform, that is how to insert an element into an heap. What happens, suppose we have a heap is there and we want to insert an element into a heap. So we will insert the element as the last element of the tree, after the last element of the tree, so that new node which has been inserted becomes the last node of the tree. But after inserting the new node, the tree may not maintain his heap properties. So in that case, after inserting node as the last node of the tree, then we have to do some operations on we have to do some changes in this heap, in this tree, so that it will be a heap after inserting any node. Now remember one thing, a new node, when it will be inserted into a heap, so it will be always the last element, and after inserting, if it does not maintain the heap property, so we have to change the position of the new node which has been inserted, so that the total tree will be a heap. For example, we will be taking example of this. Now here a max heap. Now heap is kind of a binary tree which I have discussed. So that for every node, when every node of that heap has highest value, has higher value than all of its children, then that is called a max heap. And there are two types of heap, one is max heap and another is called min heap. Min heap means if every node of the tree has the value lower than all of its children, then it is called a min heap. So heaps are two types, max heap and min heap. In max heap, every node of the tree has node of the tree has value which is greater than all of its children, and in min heap, every node has a value which is less than all of its children. So for example, here consider a max heap represented by the array 40, 30, 20, 10, 15, 16, 17, 8, 4. Now how this heap is represented? It is represented as an array, as an one-dimensional array. So here in this example, the array index has been shown here, and the value for index position, that is how to store the heap. Now we will start from the root node. which is at level 0, then we will go for next node, that is level 1, next level 1, and we will start writing the element or values from left to right. Then when the level 1 is complete, then we will go to next level, that is level 2, and again we will start writing the values from starting from left to right. In this way, the nodes in a heap are stored in an array level by level and starting from left to right, going from left to right until we are going to the deepest level, and that nodes are sequentially stored in an array. Now when we all know that array index always start from 0. Suppose there are 10 elements in an array, so it will start from 0th index and the highest index will be 9. So to store 10 elements, we have the lowest index will be 0 and the highest index will be 9, so that 10 elements can be stored in a one-dimensional array. But for some reason, that is for doing some operation, so we are not touching the 0th index of the array. There is arbitrary any value, we keep it there at 0th index of the array, that will not be any node of the tree. Then after that, from first index we will start writing the elements of the heap one by one, level by level, and starting from, for each level we will go from left to right. In this way we will store all the values, all the elements of the heap within an one-dimensional array. So for this particular example, so here array index, though the array index starts from 0th index position, but 0th index position is not used for storing any element of the heap, so that will be any arbitrary value at 0th index. So array index, if we starts from index 1 and we store the element of the heap node one by one, suppose we want to store 9 elements, so index 1, then 2, then 3, 4, 5, 6, 7, 8, 9. So these are the array index, and what are the values we are storing? At first index value is 40, then second index value is 30, then 20, then 10, then 15, then 16, then 17, then 8 and 4. So that is the heap. So if I see here, array index has been start from 1 to 9, and the value, these are the elements or values that we have stored in the array, and actually it is representing a heap. So if we want to represent it as a tree structure instead of one-dimensional array, so how that tree will look like? So we will start from first index, that will be the root node. So 40 will be the root node. Now if the position of a node is I, then I have told you that heap is a binary tree, so every node can have at most 2 children. So what happens in a heap, all of the internal level, that will be always complete. That means for any nodes in the internal level, for any node there will have always 2 children. When we are going to the last level of the tree, then it may be possible that the last node which is in the tree, that may be the only child of its parent. So but for internal level, every node will have always 2 children. So the node is 40, root node, and so the next, then we will go to, so 40 is it is at level 0. Now next it will have 2 children, so that will be at level 1, and we will start from left to right. So in left child will be 30 and right child will be 20. So 40, it has value children 30 and 20. So it is in level 1. I told you that every internal level will have always two children, but at the deepest level, last level, there may not be, that last node may be the only child of its parent. It may be or may not be. So, and when the level, one level is complete, all level is complete, then we go for the next level for node for the to represent the tree. One level is complete, then only we go for the next level. Now 30 and 20, they are only the nodes that are in level 1. Now in level 2 there will be children of 30 and children of 20. So 30 will have children, this 10 and 15. So there is another way how to find out the children, which is the children of a particular node. I'm telling you, suppose the node, parent node position is equals to I, then its left child will be at index twice into I, and right child will be at index twice I plus 1. So that is the formula. For example, 40 is the root node whose position index value is 1, so its left child is at twice I, that is 2 into 1 2, and the right child will be at position 3, which is twice I plus 1, that means 2 into 1 plus 1, which is 3. Now similarly for node 2, that position is 2, so left child will be at index 4 and the right child will be at index 5. So 10 will be left child of 30 and 15 will be right child of 30. So at level 2, 10 is the left child and 15 will be right child. Now coming to the node 20, the children of node 20 will be at which position? 6 and 7 position. So at 6 there is value 16, this is left child, and 7 there is value 17, which is right child, and they're all in level 2. Now level 2 is complete. Now we will go for the next level. So first of all we have to consider the children of node 10. We know the node 10 is at position 4, so its children will be at position 8 and 9. So its children, left child will be 8 and right child will be 4. So 8 is there and 4. After that there are no such nodes. So if we see the internal level, level 1, level 2, all are complete, but which is at last level, that is level 3, it has only 2 elements, it has only 2 nodes. So level 3 may not be complete here, but all the internal node, that level is complete. The number of nodes in all internal level is always power of 2, and in last level may not be, that level may not be complete. So now question has given that this is a heap. So how to check whether it is a heap or not? First starts from the root node 40 and its children are 30 20. So 40 is has greater value than all of its children. Now considering 30, which has children 10 15, so 30 parent 30 has greater value than all of its children. Then next node in level 1 is 20, which has children 16 and 17, that means 20 has greater value, parent 20 has greater value than all of its children. Now going for next level, and the leftmost node is 10, and 10 is a parent node which has children 8 and 4, which has greater value than all of its children. So obviously this is a heap and this is a max heap. If we consider one thing, in max heap the root node has the highest value among all these 9 elements. In max heap the root node has the highest value among all the elements of a max heap. So this is a heap. Now what is the question? We are going to the question once again. Now consider that a value 35 is inserted into this heap. After insertion, the new heap is what? So we have to insert a value 35. So already I told you how to insert a node into a heap. How to insert a node, we will see that into a heap, and in bracket I can, what kind of heap it is? Max heap. It will be a max heap. for this particular example. So what we will do, the new node which we want to insert is 35. So what will be where I will insert it first? I will insert it after the last element of this heap. So last element is 4. After that we have to insert 35, which will be the left child of parent node 15. So that will be the new node. But if you now see that every node except 15, this parent node has lower value than its children. So this is not satisfying the property of a max heap. So what we have to do, we have to convert this is now only a binary tree. It is not satisfying the property of a heap. So what we have to do, we have to convert this tree into a max heap. After inserting a new element, we have to restore its heap property. So how to restore? The element is 35, which has been inserted at the last element of the heap. Now which has parent has less value than its children. So we will exchange this position between parent and child. So 15 will come to this position and 35 will go to position of 15. So that means this node, new node, we are considering it movement upwards movement along the tree. So after exchanging their position, what will be our heap value? That will be like this. 40 is the root node, then it has children 30 and 20, then 30 will be child 10. Now instead of 15, 35 will come here as a position as a right child of the node 30. So 30 has right child 35. Now all others nodes, there will be no change. So 20 has children 16 and 17. Now 10 has children 8 and 4, and after exchanging the position between 15 and 35, 35 goes to parent position and parent on 15 comes to child position. So 15 will come here. So here that will be 15. Now consider after this operation whether this is a max heap or not. So we consider the we are now checking the position, new position of the new element. New position of the element which we have inserted 35. Now 35 has parent which is 30, which is less than 35. So what we will do, parent 30 will come to this position and 35 will go upward movement at the position of 30. So after this exchanging position, what will be the heap? 40 will be root node and its left child will be 35. Right, and all other nodes position are intact. 35 left child 10 and the right child will be 30, which has come to the position of 35. So 30 will come to this position and all other nodes we are not changing anything. Now 10 has only 2 children 8 and 4, and 30 will have now, this is the 15. Only these two positions are getting interchanged here because the parent node has less value than new node 35, the new node 35, which is the child of the parent 30. So we will move upward 35 and the 30 will be going to the child position. Now whether this is a heap, now consider this node 35. Now 35, now this parent node is 40, which is greater than its greater than child node 35, and as we have not touched any other node, all are in position. So we can say now the heap property is restored, and that is the final heap after inserting new node 35, and new node will be at this position. So 40 is greater value than 35, 20. 35 has greater value than its children 10, 30. 20 has greater value than its children 16, 17. And 10 has greater value than its children 8, 4. And 30 has greater value than its child 15. So now if we represent this heap in an one-dimensional array, so what will be the array index? 1, 2, 3, 4, 5, 6, 7, 8, 9. So the array index position 1 2 3 4 5 6 7 8 9. So we will start from index 1, we will start from root node, and after each level is complete, then we will go for the next level and we'll store the elements starting from left to right for that particular level. When that level is complete, all nodes have been inserted, all nodes have been has been shown in the array, then we go for the next level of that level. So 40 is at position 1, then we go for level 1, and the nodes will start from left to right. So 35, then 20, 35 and 20 will come here. Then we go for next level, we'll start from left. So 10, 30, 16, 17. So here it will be 10, 30, 16, 17. So this level is complete, so we will go for the next level and we'll start scanning from the left to right. So 8, 4, 15. So there will be 1 minute, 3 4 5 6 7 9. So there are 10 elements because we have inserted a new element. So after that, before it was a heap of 9 elements, now after inserting a node, it becomes a heap of 10 element. So we have completed up to this level 17. So next node will be 8, 4, then 15. So here will be 8, and this 4 and 15. Now that is the heap that is represented after as one-dimensional array. Now this is our result. Now going for the question. So now consider that a value 35 is inserted into this heap. After insertion, what will be the new heap? So one of the value has given. So what are the options that I'm writing here? First 40, 30, 20, 10. So I'm writing the option first. 40, 30. There are 4 options: 30, 20, 10, 15, 16, 17, 8, 4, 35. This is option A. And option B, what are the array elements? 40, 35, 20, 10, 30, 16, 17, 8, 4 and 15. Then what will we see? 40, 30, 20, 10, 35, 16, 17, 8, 4, 15. And option D, 40, 35, 20, 10, 15, 16, 17, 8, 4, 30. So we will go to our answer, what we have calculated. We have calculated here that is our answer we have obtained. So 40, 35, 20. See option E, there is 40, 30, 20. So option A is not correct. Next go for B, 40, 35, 20. Then 10, 30, 16. Then 17, 8, 4, 15. This option B is a correct option. That is this array that is in at option B. And if we go for other options, suppose C, 40, 30, 20, but here is 40, 35, 20. So option C is not also correct. And if we go for option D, we can find that 40, 35, 20, then after 10, 15 is there in this option. But here after 40, 35, 20, after 10, 30 is coming here. Here it is after 10 it is 15, and after 10 here it is 30. So this is D option is also not a correct option. So correct option is only B. And this heap, and how to, by seeing that array without drawing the tree or drawing the heap, by seeing this array also we can say whether that sequence of nodes are representing a max heap or not. For example, if we go for this, for option A, so first node is 40, which has children 30 and 20. So 40 is greater than 30 and 20. So node 40 is satisfying the heap property. They satisfying the heap property. Okay, then node 30, whose children is 10 and 15. So node 30 is satisfying the heap property 10, 15. And then node 20, whose children is 16 and 17. So 20 is also satisfying the heap property. So 16, 17 is its children. Then next node is 10. 10 has children 8, 4, which is satisfying the heap property. So that is okay. Then we come for 15. 15 has only one child 35, which is less than child 35. So this node 15 does not satisfy the property of a heap, so it could not be a heap. This sequence of nodes cannot represent a heap. Instead of that, if we see the option B, if we see that this node 40 has children 35, 20, which has greater value. Okay, which has greater value. Then node 35 has children 10 and 30, that is greater value. Then node 20, which has children 16, 17, which has greater value than its children. Then node 10, which has children 8, 4, so this has greater value. 10 node satisfy the heap property. The next node is 30, which has only child 15, which is greater than its child. So 30 also satisfy the heap property. So in this way also, by seeing the array, one-dimensional array, instead of drawing the tree structure, but just by seeing the array elements also, we can find out whether this array representing a heap or not. And obviously either it will be a max heap or it will be a min heap. So that is the way how to, in this way we can see how to insert a new node into a heap. But suppose the heap here first, this heap already was created. So for inserting a single node here, to insert a single node into a heap, what will be the factor, what will be the number of the operation, inserting a single element, what will be the factor of this operation, upper limit of this operation, number of how many, what will be the factor, that is called number of steps to be executed, maybe number of steps, and each step number of times, how many number of times is getting executed. So in that case, suppose when we are 50 inserting a new element, it will check with always all its parents, then again it will check all its parent, now it will then again this level node will check its parents actually. So how we are traversing level by level. So the number of levels will be what, as it is a binary tree, if there are n elements, so number of levels will be log of n. So so the operation will be a factor of log. Inserting a single element, the operation will be a factor of log n. That means maximum how much time it will take to insert a new node into an array of n elements. So it will take a maximum a factor of log of n. Log of n, why? Because that is depends on the number of levels, as it is a binary tree. The number of levels, if there are n total nodes in the tree, so number of levels will be log n. So that is a factor. Now suppose when we were inserting an element one by one, suppose we want to insert 16 elements or 8 elements one by one we are inserting. So what will be the factor? The operation will be a factor of how much for each inserting each element we have to do a operation of maximum operation of log n. So for inserting n elements we have to do operation, the factor will be a factor of n log n. So when a single element is inserted, so the operation insertion operation for a single node will take a factor of log n, will take time which is a factor of log of n. And for inserting n elements, each element will take a maximum a factor of log n. So n elements will take maximum a factor of n log n to insert n elements into a heap. To insert n elements into a heap. So n log n, it is a factor of n log n to insert n elements, and to insert second element it will be order of a factor of log n. So in this way we can insert a new element into a heap. And here also one thing I told at the beginning, so if a node is position I, then its left child will be at position twice I and right child will be at position twice I plus 1. Now if a node which is at position I, so its parent node will be at position I by 2. For example, this node 8, suppose this seventh location, seventh position node is 17. So who will be the parent of this node? Now 7 by 2, that means 3. So 20 should be the parent of 17. Now if we see the this heap, that the 17, the parent node of 17 is 20. So by just calculating the position index of the array, we can also find out that which node is parent of a node or which node are child node of a node. In this way we can find out. Okay, thank you.